we just talked about the cross product between two vectors A and B and how we could relate that to vector C. So in this video, what we're going to be talking about is how we can use the cross product to calculate our moment about any point in 3 dimensions. So if we want to determine what is our moment about the origin for any vector, what we can do is we can define for any force that's in space. Alright. We can calculate the distance from that point O to our where our force is being applied. Alright. And that distance we can define using a position vector, vector r. Alright. And then if we take the cross product of vectors r and f, what we'll end up getting is we'll get a couple moment, or we'll get a moment at point O. Alright, that will be perpendicular to both r and f. Alright, so the magnitude of our vector is going to be of MO. It's just going to be the same as the formula we had for a cross product, where we took the magnitude of our position vector times the magnitude of our force times the sine of the angle between the two of r and f. And then the direction of our moment will be perpendicular to both r and f. So the last thing is going to be an important thing to think about when you're trying to calculate your your moments using this equation is the principle of transmissibility. So what the principle of transmissibility states is that you can choose your position vector to simplify your calculations as long as it lies along any point where the force is being applied. So if you were trying to determine, for example, you want to determine the moment about the origin of a force that's applied to the body at this point, and you know the force's direction and you know its magnitude, you can define the position vector from the origin to the point where the force is being applied here. All right. Now, so you can say in this case that the moment about point O is going to be equal to R1 cross F. Now, what you can also do is you can draw your position vector from the origin point to another point where the force goes along. Right? And we can call this R2. Right? And we can calculate the same moment using the second position vector. So this would be R2 cross F. Alright, and then the last one would be, we could also define it at another point. So this should be R3. As long as that it starts at the origin point and it ends at the force vector, you are totally fine to define the position vector at any point along that along force F. All right, as long as it ends at point O. All right, all three of these would generate the same Cartesian vector. So pick the position vector that makes your calculations the easiest, as long as it lies along the force vector. All right. So if we go on, so we can define our position vector using our the cross product between. We can define our moment about a point using the cross product between R and F. So we can write this using the determinant of a 3 by 3 matrix, just like we did for the cross product between any two vectors. So to take this cross product, we can rewrite the first two rows, our two columns of our equation of our matrix here. All right, we can then take the cross product between the two. All right, and then so we'll get 6 terms out of this using the 3 diagonals. So you can rewrite m naught as being equal to it's going to have 3. So it's going to be a Cartesian vector output with components along the x, y, and z axis. So if we look at the diagonals from the top left to the bottom right, we'll get ry times fz times the unit vector I. We'll get rz times fx times the unit vector j, and then we'll get rx times fy times the unit vector k. And then we go back here, and we'll get r minus ry times fx. We'll get r minus rz times fy, and then we'll get rx times fz for I'm sorry, I made a mistake here. So the first diagonal we get ry times fx, that should be multiplied by the unit vector k. You get for the unit vector I, we get rz minus fy, and then for the last one we get minus rx times fz times the unit vector j. Okay, so what this you'll have is it'll have our unit vector will have its x component, it'll have its y component. I'm sorry, the moment about point O will have its x component, its y component, and its z component here. Alright, so this would be our moment about the x-axis, moment about the y-axis, and moment about the z-axis. So the last thing is if you want to find the resultant moment for a system of forces. So if you have multiple forces being applied at the same origin point, what you can do is you can sum up, you can calculate each of the moments individually, and then you sum up their components to determine the final moment. So what this would be is we would have for the amount of cross products that we need to calculate, that if we sum all those cross products individually, we would get our moments. So if you had 3 moments, for example, so if you had moment 1 plus moment 2 plus moment 3, you would get the overall moment about the origin point would be equal to r1 cross f1 plus r2 cross f2 plus r3 cross f3. Alright, so each of these will have their own individual x, y, and z components. So you just add the x, y, and z components of those 3 moment calculations to get your overall moment about that point.